So good morning. In today's lesson we're learning all about hexadecimal. So by the end of today's lesson we want to know what hexadecimal means, why we use it, and be able to convert in both directions to and from hexadecimal from binary. Note you don't at GCSE level have to go from denary to hex. You can, and we probably will do some examples today, but the easiest way to do that is to go from denary to binary and then from binary to hex, because binary to hex is dead easy, hex to binary is dead easy. That's what we want to work through today. So 5 seconds from now. Did you write it down? Okay, so now that you know it's coming, people at home have an unfair advantage because they can pause the video. You will have 5 seconds to write down this binary number. Anyone who can do it perfectly will get a class charts positive. Are you ready? Go. All right, anyone think that they've managed to get it? For the benefit of people at home, there was lots of frustration and complaining. You're absolutely right, those of you who have said, this is just to prove a point that writing down binary is great for computers, but it's rubbish for human beings because there's just too many digits to process and there's too much chance of us getting it wrong when we copy it down. So hex is designed for humans, not for computers. Remember, computers can only understand binary because computers understand zeros and ones, off and on. Yes, we can program them to understand hex, but it's not their native language. It's like an English person going to China. They don't understand anything until eventually they pick up Cantonese or Mandarin. You can train a computer to understand hex, but only by teaching them how to translate it into binary. The same with an image. A computer doesn't understand an image unless we train it how to break it down into binary. So the alternative solution is in hex. Let's have a look. Denary is designed for human beings. It just seems to work. It's not the only counting system that we have, but it tends to be the one that most civilizations used. There are ancient civilizations that used a different base number, but it works for us because we've got 10 digits, as in fingers and thumbs, and 10 on our toes. So we could really, I suppose, if we were really mathematical and we didn't wear shoes, have a base 20 number system where we could count with both our fingers and our toes, but it's a bit confusing. The idea is we've got 10 digits to work with, as in you've got 10 here, but if you go on to any more, a larger number, you can still have a larger number, but it requires 2 digits of denary. And binary is the same kind of thing, but with base 2, as in you've only got 2 digits to work with. And if you need a bigger number than 2, as in 0, 1, a bigger number than 1, you have to use those digits more than once. Hex is a nice way of compressing it so that it takes up less space when you write it down on paper, but notice, or it's important to remember, it still takes up the same amount of space when you save it on disk. As in, hex doesn't magically reduce space on disk, it's still using the same number of bits, it just allows you to have more symbols. So that's what the base number means. So you have a little number down here, we call that the base. 10, base 10, means a denary 10, which is 1010 base 2 binary, because 1, 2, 4, 8, 2 plus 8 is 10, base 10 in binary. And then in hex, it's just saying that 10 in hex, denary 10 in hex, is A. So we're saying on this table here, after we get to 9, instead of going up to 10, we just write the first 6 letters of the alphabet. And that's it. That's all we need to do. And it's actually dead simple to work out. So we can have any binary number. And the beauty of hex is, because it's base 16, each nibble in binary can have a number between 0 and 15, as in 16 different possibilities. So if you take an 8-bit binary number and chop it in half into 2 nibbles, each nibble is going to be a hex character. So let's have a look and work through this. Whoa, where's my whiteboard gone? So if we take a binary number, it would be nice if it was the same one, 0110, 0110, and 1100. Split it in half, so we've got 2 nibbles. And then each half you work out as denary. So you do 1, 2, 4, and 8. 1, 2, 4, and 8. If people are going to make a mistake, they'd probably try and work it out as an 8-bit number. 1, 2, 4, 8, 16, 32, blah, 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 blah. It's easier than that because we only have to deal with numbers up to 16. So then you work out what you've got. So 4 plus 2 is 6. 8 plus 4 is 12. Now 12 is 2 digits. We can't have that. So 6 in hex is just 6. It's 1 digit. But 12, we need to work out what that is in hex. And I'd always recommend you write down, whenever you see a hex question, A, B, C, D, E, and F. And then next to each one, you just start from 10 and go up. Some of you will remember it, but under pressure in an exam, you might remember it wrong. So I'd always recommend writing that little table. And then you just read it off. 12 is C. So 6C in hex is this number in binary. And if we wanted to work it out in denary, you take it as an 8-bit number. 1, 2, 4, 8, 16, 32, 64, 128. And that's going to be, what, 64, 96 plus 12 is what? 108. Yeah, thank you. So you could, if you wanted, if you're really good at your 16 times table, do 16 times 6 plus 12. But because we're not that good at our 16 times table, I wouldn't bother doing that. If I was implementing it in Python, I'd do it this way. But the way to do it as a human being and in an exam where you're not allowed a calculator is to just break it down into nibbles and do each nibble separately. So we just had a great question. Where do we get the 16 times 6 from? Because this nibble has been shifted across by 4 bits. As in, you remember your arithmetic shifts and your logical shifts. If you shift left, you double. And if you shift left 4 times, you double, you double, you double, you double again. It's by multiplying by 16. So that's why it's the 16 times whatever value this is. But I wouldn't remember that. I think that will confuse you. I think what you need to remember is, let's have a nice simple one. 8-bit number, you only need to deal with 8-bit numbers in your GCSE. Split it up into 4 nibbles. Work out what each nibble is separately. So that's 1 and that's 8. So the hex is just 1/8. Easy. With no symbols in between. Sometimes you'll see it written as 0 times 18, or occasionally, and more likely in an exam, you'll see 18 base 16, because we need to make sure that that's not a denary 18, because they're different things. So this would be nice and easy to work out what it actually is. That would be 1 times 16 plus 8 is what, 24? Let's prove it. 1, 2, 4, 8, 16. Can't be bothered to do the rest. 16 plus 8 is 24. So it does work. You want to go the other way, so let's go for E2 in hex. It's the same process, but in reverse. Each character in hex is 1 nibble. So you write down that magic table, A, B, C, D, E, and F. If you really want to, you can write down 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, but there's no point, because a 9 in hex is a 9 in denary. So A is 10, and the maximum is 15 for an F. So E is 14, 2 is just 2, and then we work them out as a 4-bit binary nibble. So 1, 2, 4, 8, 1, 2, 4, 8. 14 is going to be, well, 8 plus 4 is 12, plus 2, so 1, 1, 1, 0. And then 2, now we have to be careful to do it as a 4-bit nibble. As in, we have to write all the bits, and then E2 in hex is all of those bits together. Does that make sense? Okay, let's go back to the PowerPoint and see what it says. Blah-de-blah-de-blah. Yeah, I think that makes sense. So hopefully we're going the other way now. We've got BE here. First step, work out what all of the letters are. So A is 10, B is 11, and then E is going to be 15, because E is the is that right? I don't think that's right. No, I think that's wrong. Because, let's write it out. A, B, C, D, E, 10, 11, 12, 13, 14. F is 15. That is wrong. So yeah, if that was an F, this working out would be correct, but this slide is wrong. So this person who put this slide together was in a bit of a rush and thought, oh, it's easy. But they made a mistake. They didn't write this table out, so they made a silly mistake. So that's useful, it proves a point. Always write the table out. Where's it used? Well, I think we can just jump straight in to activity 1 on P10. I would recommend having some paper for this, but when you get the hang of it, it's nice and easy. You just split it up into nibbles. So a 0 is going to be a 0. And these 4 bits here, I need to enable editing, I can't write it down. 1, 2, 4, 8, it's just going to be 8. So that first one is going to be 0, 8. See how you get on. So there's one more thing I want to show you. This isn't to do with computer science, this is more to do with words. So you work out the answer, the first 4 bits are 0, the next 4 bits are 8, so the answer in hex is 8. But you need to be clear that this is hex. So in an exam paper, I would always write base 16. But in Word, that looks a bit difficult to do. So there's 2 keyboard shortcuts worth remembering. Control-Shift equals does a superscript, as though it's 8 to the power 16. That's not what we want. We want Control and equals for subscript to take it down. That is what we want. So that's Control and equals when it's selected. This says that this is not 8 in denary, this is 8 in hex. So I'd even like you to do that for the ones that are there. Control and equals, turn those into hex numbers so it's crystal clear, even though it says hex above. Sometimes it's obvious because they have letters in, but if they only have numbers in, it's ambiguous, so you don't know. Ambiguous means more than one possible meaning. I'll just do one more while we're here. So 0 is going to be 4 zeros. You're going to write out on paper all of your letters. So you're going to have A is 10, B is 11, C is 12, D is, what did we say, 13. So you need to have 13 in binary, which is going to be 8 plus 2 plus 1. Fab. See how far you can get. So we're going to go through conversion from hex to binary again. So first step, write out your hex. Second step, write your little table. So A is 10. And then if it's just a denary number, then in denary it's the same. If it's a character, you have to use your little table. So F is 15. Then we need to work out what each of those are as 4-bit nibbles. So it's probably worth writing out the placeholders. 6 is going to be 4 add 2. 15 is going to be all of these numbers added together. So in binary, you just read off from left to right the whole thing, and that's your binary number. So for activity 3, we want to learn how colours work, because colours is one of the examples where we use hexadecimal quite a lot as programmers. So we can see a hex string here for the pen colour, that's somehow green, and this is kind of the fuchsia pink. We want to understand where that comes from and how to make our own. So the idea is most colour systems on a computer are RGB, as in the monitors you're looking at on your phone or on your laptop or on your desktop. Each pixel will be split up into a red light, a green light, and a blue light. If you switch all the lights off, it's black. If you switch all the lights on, it's going to be white. If you just want red light, you just switch the red light on. And if you want yellow, it's a combination of 2 different colours. So you have 2 hex digits for the amount of red light, 2 hex digits for the amount of green light, and 2 hex digits for the amount of blue light. So if you wanted black, then in hex, you'd switch all the lights off by saying 0, 0, 0. And another 0. If you wanted white, you'd switch all the lights on with FF, FF, FF. You often put a hash in front so that we know it's hex. And if you just wanted green, because it's RGB, if you wanted bright green, you'd switch the red and the blue off and you'd have full-on green. And if you wanted dark green, you could just have a smaller number for the green. So 0, 0, 0, 0 for blue, and I don't know, maybe like 9, 9, something like that. So you can play around with any of these hex codes to get any colours you like. Let's just test it and see what that looks like. 0, 0, 9, 9, 0, 0. We should have a dark green in the middle. Yeah, good. So work your way through, and there are a couple of numbers, a couple of activities to work through. So the last extension challenge today, if you get onto it, is to try and write a Python program that will draw a line in each of the colours of the rainbow. So I remember it as Richard of York gave battle in vain, red for Richard, for orange, York for yellow, gave for green, battle for blue, indigo, in, vain for violet. But Richard of York gave battle in vain. Whatever mnemonic you use to remember the colours of the rainbow, or if you just Google it, I don't really mind. Try and draw a line in each of those colours in Python using your turtle graphics, and that's the last extension. Then just upload this on the data 2 section, and that's it for today. Well done.